Hello and welcome back to another installment of our MATLAB tutorials. Today I will be telling you how to do an FFT. So now I'll start this off by saying this stuff can be FFTs. If you go and look it up, there are several ways to do this, and they all have distinct uh, positives and negatives to them, or disadvantages and advantages. But for this one, I just picked a basic run through, just to try and show you guys what I did for a simple FFT. And FFT stands for a fast Fourier transform. Now, this shows our magnitude over an FFT shows us our magnitude versus our frequency, and so you can go more in depth about what an FFT is, but this is pretty much just to show you how to do it. So going back to our graphing figure, if we see that our uppercase Y is our Y data, we want to little sneak peek, but we want to show you, because Y is our horizontal distance, and we want to those are the values we care about, because we know that X is just time. It's 0.1 step up to 10 from 0, so we don't really care about that. What we actually care about is that horizontal distance, and so we then want to do an FFT on it. And so we want to find the length of X. We see some of those commands from the beginning showing up, so they are very helpful, and you do use them a lot. So we want to see the number of elements in X, because that is going to help us find our f sub s, or our sampling frequency, which we need to do an FFT. Now, I just hard-coded in 101, but realistically, our frequency sampling, our sampling frequency is our number of elements over time. So it's total elements over total time, which would give you a value in hertz. So that's what we sampled at, and we want then in here this is just for our so we take an absolute value, because in actuality an FFT is usually non-symmetric, and it is symmetric, and we want to make it non-symmetric. So by taking an absolute value, we're just looking at 1/2, and that helps us because we don't want to see the same thing twice. It's just our same data flipped or mirrored on the other end of our graph. So we just want to take the absolute value. We also want to denote a new probability, not probability, but we want to denote just a new different area underneath. And so that's what we're doing here. I don't want to get too in depth with it, but if you take this code and go and use it, it will it will help you out. So let me see if I can find some more definitions on how to help you out. But yeah, the end function is just it's the end of our graph, so it just stops it. So it takes us all the way, and then subtracts 1, takes us all the way, subtracts 1. So then this is our frequency. I'm not going to go into how you calculate all the frequency, but basically we take our sampling frequency and multiply that by over a relationship of our just a step of half of our length, and then take all that, divide by our length. So that's just kind of a little of background, so I'm not just hitting run and you see what pops up. But basically we're going to want to plot our frequency versus our P1, and that is going to show us our FFT. We can title it, do an X label and Y label, just like we did in our regular graph. We have our units of frequency, hertz, and we know magnitude is unitless. So we run this, we can see we get our first graph just from the open object command and stuff like that that's already in there, and then we get figure 2, which is our FFT. Now, realistically, we probably shouldn't see anything, because this was a symmetric plot, as you can see from Y sub t. So maybe X sub t would have been better, but that's also we wouldn't get too much. This probably isn't the best example to do an FFT with, but the point of this was just to more so get across how to do an FFT. So hopefully this helps. We see in using an FFT, it's not exact in MATLAB. It's not ideal, is the thing, and once you learn more about FFTs and filters and all that, we'll find out why that is. But for the sole purpose of this video, is to tell you how to do an FFT. We see that R0 is our highest magnitude, and that is consistent with us being symmetric. So we know that it looks congruent with what we would expect. Again, we can go and pull across. We see that it levels out after a while, and so yeah. So again, oh, another cool thing I probably didn't talk about in the graph video: if you pull away and then go hit home, it'll take you back to what you had previously. So I think that's all that I wanted to cover as far as a fast Fourier transform in MATLAB. Like I said, there's many examples that you can find online that'll tell you how to do an FFT, and again, each one of them has their advantages and disadvantages. Like I'll say, just for reference, like for this one, an advantage is this. This is your real data. So this is just an FFT of your actual data. A disadvantage is it may not look the best. So not look the best, but it may. Yeah, I think that's the right term. It may. There are some that make your graphs look nicer. This is kind of, like I said, it's not ideal, so that comes into play with this. You can't find ones that are close, but for this one, not so much. Some other functions, just to name a few, is our p-welch command, and we can go into just help p-welch, and I'll show you. That's just another command so that you have those tools in your toolbox to be able to use. Basically, p-welch is kind of like an average, so it also, you don't have to take this absolute value. It'd just automatically make your graphs non-symmetric. So you can use the p-welch command in MATLAB, and that's kind of the point of all this, just to provide you with the tools and then give you the resources to be able to take this information and really run with it as far as you can take it. So I think that is all that I wanted to cover as far as fast Fourier transforms. Like I said, this is a very broad overview of a very in-depth topic. So don't take this as the only way to do it, but do your research and just know that this is one way to do it, and know about your commands. All right, thank you. Good luck.